Alec could give the last lecture of the shorter course.
Oh, okay.
This was supposed to speak tomorrow.
Tomorrow.
We'll talk tomorrow.
So tomorrow, Nick will talk about.
Is it a continuation?
Yes, it is a continuation.
Fourth part. Okay.
So Nick will talk about the thin obstacle problem. So on my part, the obstacle were real graphs. So Nick's case will be something like this. And then you have, this is the obstacle. So it's very thin. And that makes a lot of trouble. So I'm happy that I skipped that. So we can do it. At this third lecture, I will discuss now the regularity of the solutions. But before doing that, we need one, let's call it tiny result, which is called classification of global solutions, in order to be able to do the local analysis. So partly this will be from very close to what Eugen did for an hour ago about the classification of homogeneous global solutions. So I will try to skip uniform results. So I'm skipping two things. One is the uniform result, because that requires a lot of work to do it. I will tell you what that means. The second one is that I'm not doing the C1 regularity of the free boundary, but only Lipschitz. But you will see from what I get, you also can get C1 regularity, because if your Lipschitz norm is almost 0, then you get C1. So that is actually in the proof. But then it is not uniform. That's again a problem. So the regularity I get depends, so the C1 norm I get depends on the point also. But generally you don't need this. You can make it very strong, much stronger than what I'm going to do here. This is an easy way out anyway. It at least gives you the ideas behind it. So as I discussed it, I think yesterday, we have possibilities that can appear, or of free boundaries are the following. The cardioid, I had an example with a cardioid. So this is cardioid. And then there is a, here U is negative, here U is positive, here U is positive, here U is 0. And this all satisfy the same equation. Laplacian of U equals the characteristic function. And U, the gradient of U is 0 in omega complement. So this is omega complement, and this is omega. And the picture is something like this. Okay. The second example that, so this is a worrying case for us. We don't know, I mean, this is not a regular free boundary. It's not a graph unless you try to see it from certain points. But one can actually prove in 2D that these are analytic curves. But that requires a lot of work. But so I'm going to skip this. So that means that at least I'm assuming that the complement is thick. And then the second example was functions like this. And this gives you a solution which grows quadratically, and then it is 0 here. 0, and then it's like x1 plus. Okay? And this is a very smooth graph. The free boundary is a plane, n minus one dimensional plane. So I'm hoping that I will pinpoint and try to find in my local problem points that asymptotically behave like this. Then the question is whether I can prove that they locally behave like this, like a C1 graph. So if I scale it, it will be a plane. And then the second example, or the third example, were points with, when you blow up, you get polynomials. So any polynomial p of x with Laplacian of p is just 1. These are also possibilities. Because you blow up, you get either one point or just a line in 3D, let's say, and many other varieties. So I don't want this. These are not good. These are not good for me. So I'm going to stick to this one. And therefore, I'm going to assume something about the complement. So we assume generally assume something about omega complement, let's say at L0. It should be thick. So whatever that means. Okay, so before going into that, let me introduce a monotonicity formula. I did one, we called it ACF. I will do a second monotonicity formula. We call it Weiss monotonicity formula. This comes from, I think, harmonic mappings, related to harmonic mappings. This was also done of somebody else. I don't remember the name right now. OU. The name is OU, independently actually. It was a former student of Avner Friedman, if I'm not wrong. But they were doing this independently. So the Weiss monotonicity formula is this. This goes not for the derivatives of the function u, but the function itself. So it's like a frequency, but not exactly the frequency, but almost like a frequency. So you take the energy. So this is the energy. So Laplacian of u becomes the characteristic function of omega, and then you go over the ball of this, and then you have a balance here. So you balance it with minus 1 over Rn plus 3, sorry, 2 divided by n plus 3. So there should be a 2 here. And then integral of u to power 2 on the boundary of the ball. The same ball. Okay. So you take the energy and you balance it with the surface integral u to power 2. So what happens is that this function is, our function is monotone. Theorem is W prime in R is non-negative. You can actually prove this very easily. It's, I would probably say 5 minutes work would be enough for you. Proof is this, is W R U x 0 is exactly W1 UR 0, where UR is the scaled function. Okay, so it scales like this, and now you take the derivative. Because you see there is no derivative of the integrals itself, but you go inside the integral, you have the function UR to make the derivative of. And then integrate by part. This is what you do, nothing else. You will actually end up at W prime, so you're going to get that W prime R, if I'm not wrong, is 1 over R with some constant maybe, and then UR prime to power 2 over the boundary of 1. Is that? I think this is something like this you get, or something. Something like this. It becomes monotone. Maybe I have it here. Okay. So, since this is monotone, it gives you homogeneity of the global solutions, of the blow-up solutions, not global solutions. Let me just say one word about blow-up solutions and global solutions. There are two different things. Blow-up solutions are those that you scale one function and you get a solution in Rn. Global solutions are solutions that already exist. They are not necessarily coming from a blow-up. And if you want to see an example for this problem, you can think of this. You take a plane a plane solution like this, one-dimensional, this is a homogeneous solution which is coming from a blow-up of a very smooth point. Take any smooth point and blow it up, and you will have this solution. You can have another example, which is the one I gave you at the beginning of the last lecture, and it was A times x, A plus B x minus, let's say, origin, 2 minus n plus x 2 divided by 2n, and you take this in outside the ball in BR complement. R is chosen appropriately. R, A, B are chosen in a way that this function becomes 0 twice on the boundary of the ball R. So the solution will be something like this. And this is a solution to our problem. It's a global solution. It is by no means homogeneous. So they also exist. You can actually take any ellipsoid, and outside that there is a solution. You can take a cylinder. Outside that there is a solution. You can take a parabola. Outside that there is a solution, actually. There is open question whether these are the only solutions, global solutions. You can classify them or not. And in 2D that is solved, but in higher D it's open question. So blow-up solutions, those are those that are coming when you scale, you get homogeneity. But global solutions are those that already exist, they are not homogeneous. So you see that classification of global solutions is very hard. So what one does in order to get uniform estimate, you have to classify global solutions. Since that is very hard, you go for only convexity, uniform convexity of global solutions. That actually helps a lot. That was the original ideas of Lewis, to do classification in terms of convexity of global solutions. Okay, so let me continue. So this is non-negative W prime, so it means that it's monotone, and then we have the following: homogeneity of blow-up solutions. So globals are not necessarily homogeneous, but blow-ups are. And here is the simple proof. So you start with any value for the limit 1. So U0 is for any sequence, let's say. So take the limit, R goes to 0, you have a solution. You take, of course, a subsequence of that. So whenever I write this, I mean a subsequence. It can be any subsequence, doesn't really matter. Here, so that you get, this is like leave R goes to 0, WS, and UR, and still a X0. And now I'm using this scaling here. So this is like lim R goes to 0, W. So instead of, this was 1 there, now it's S, doesn't really matter. You get S times R, and you get U, and you get X0. This is what you get. And since W is monotone in R, as R goes to 0, this goes to the value W at 0 plus. So this is equals W 0 plus, which exists because of monotonicity. Because of monotonicity, this exists. So it means that WSU0 is exactly W at the point 0 plus for a blow-up solution.
it, isn't it?
Yes.
Yeah.
Sorry?
That's it.
That's it.
Uh-huh.
So blow-up solutions are homogeneous. Well, probably I should have said something like that. If W prime is 0, then U is homogeneous of degree 2. I should add to this, which is actually comes out natural in the proof of. So this is the reason I can conclude it.
Formula for W prime.
Yes, this is exactly the formula. This is exactly what it is. If this is 0, then it means this is homogeneous. This is 0, so it means homogeneity of degree 2. Okay, so that was the proof. That was the proof of homogeneity of global solutions. You saw that it was a little bit maybe not that harder, but in Eugen's proof it was, because you cannot really take the derivative in that sense, because the functional is not differentiable inside. But here, the function is differentiable, so that's a bonus. Okay, so so now it comes to the fact that I want to pinpoint, I want to find all points that when I blow up, it will be like this. And I want to see, because these are the only points basically that I get regularity. And how do I do that? So I need a classification of global solutions, blow-up solutions, or global solutions that are homogeneous, and see what they are. And it shows itself that there are just two possibilities. One is the plane, this is homogeneous of degree 2, and the other one is the polynomials. All polynomials that satisfy this are also homogeneous. So how do I find that if I take a point on the free boundary, which category it belongs to? Then what I do, I compute the energy. And it shows that the energy actually is going to be, let's say, 1/2 here, and it's going to be 1 here with a constant. So it's going to be alpha n divided by 2, and it's going to be alpha n. So the energy here, the Weiss energy, is twice this energy. So it means that if I have a point with this low energy, so low energies are very good. These are regular points. And you see that there cannot be even higher energy coming to this because of upper semi-continuity of the functional. W is upper semi-continuous. So no points of high energy can come close to the low energy points. And that tells you already, once you have a low energy point, uniformly, depending on the point, you have actually no other points, but all points are regular.
Can't you use Almgren's monotonicity? I mean,
They give the same information, probably.
well, I mean, if you get homogeneity 2, then you are in the polynomial case. And if you get homogeneity,
I get always homogeneity too. The only thing is that in one case I get half of the function, in another case I get both sides of the functions. So the value will be twice. It has nothing to do with the degree. Degree is always 2.
but this case, the plane solution, that's as vanishing density, right?
This one,
Uh-huh.
what do you mean vanishing density?
Those are singular points.
No, this is a good free boundary point. If you look at it from here, it's a graph. This guy is a graph.
Uh-huh.
So it's a good free boundary point. But these ones are lower dimensional. So I cannot really find I cannot make it as a graph.
The question of homogeneity of the limit, of the blow-up limit is, let's say, difficult, and it needs this analysis just because we can pass the limit as r goes to 0 for a subsequence.
Yes. On any subsequence.
No, I mean,
Doesn't really matter.
if for all r was going to 0, it had a limit, then we would not need these difficult things. It would be clear that it's homogeneous just by the definition of the
I don't
blow-up.
understand it. Why do you say, how do you know it's homogeneous? It goes to a limit, but you don't know what the limit is.
Yes, but you are of. I mean,
No, you have a limit. You don't know what the limit is. No, I don't think you can get
No, but
cheaper than
because
this.
you are, let's say, gamma x is equal to gamma power 2 u r gamma x. I mean,
Okay, now you go too fast for me.
no, I mean if you write, it's okay. We can discuss it later.
Yeah, I don't see any other way. I mean, there is another way of doing homogeneity of the blow-ups, which goes back to a paper by Sprook. I think it was 80 something, maybe also paper by Alt. So, but they use a different type of monotonicity. They work with the function itself. It's actually a nice piece of work also, but it didn't develop that direction. So people started working with the functionals.
Where did you use the thickness?
I haven't used it yet. I just give you a heads up at the beginning.
Another question. The fact that there is a blow up, the homogeneity of the blow up doesn't say that homogeneity is 2.
It says homogeneity is 2 because of this.
It is 0. If the limit is 0, if y prime is 0,
If w prime is 0, then you see that this is going to be 0.
Yeah.
And when the derivative of u is 0 with respect to r, that's exactly homogeneity 2. So if you take the function ur, and you take the derivative, and that's 0, that shows exactly homogeneity of degree 2.
you know that w prime is missing something.
No, you have to write the formula for W prime. I mean, it's the same formula that Eugen wrote.
Yes,
but
I mean, if you, this is w, you take the derivative, and it boils down to something like this.
I believe you that.
Okay, so this is 0. It means that this integrand is 0.
Why should the derivative be 0 at 0? You show that there is a.
You mean you're talking about this one? Well, I say that this is this is monotone, so w must have a limit. Okay, so when r goes to 0, this guy goes to 0, then I will have a limit. So this is a limit value, which is constant. So it means w of u0, depending on x, is constant. The derivative of w must be 0 now for this particular function. Okay, yeah, I see your point. So let me just repeat that. So I get the w is going to be constant, so w prime is going to be 0 for this particular function, the blow-up function. So it means that this function must be homogeneous of degree 2. Okay, so the next point is, we call it balanced energy. So at any point is lim r goes to 0. So basically the value of this w Weiss energy when r goes to 0. What is that value? So this omega x0 is upper semi-continuous. So this means basically lim sup ux, x goes to x0, is less than, not u, but omega. So this means that if you have small values, large values cannot come to that. So one can compute this. So let us say alpha n, and we define it as WR U0. So we set if U is a polynomial, let's call it P. It's not as if P is 1. So P looks like something like this. So take a polynomial, then you will have a value for this, which is this alpha n, and then alpha n half is going to be exactly the half space solution. The W or let me write it, spell it out. So for this function, or any rotation of that. So all rotations are giving the same value. You can actually see that this is independent, alpha n is independent on P, but depends only on the dimension. So this is a little bit of exercise. Just compute the energy. Put the polynomial, integrate by part, and use the Laplacian is 1, and then you get actually just one constant. You can actually get that alpha n is a polynomial, something like this. Or generally you get that the Weiss energy, is going to be U0 in homogeneous cases. In these two cases, well, this is always so. Always so. And of course, if U0 is polynomial, by rotation you have the same thing. Well, this is just one line computation, so I'll leave it out. Okay, so I talked about two different points. This type of points that will blow up to a plane, and this type of points that will blow up to lower dimensional planes, or points are lower dimensional curves, straight curves. The question is, do we have other type of points? Of course, because we're talking about blow-up solutions. I just gave you examples, but they're not necessarily the only ones. You might have a lot of other things. So that's another part of the word. You have to say that these are the things you get and nothing else. So let me just write it down. It's a question. Sorry. So it's a question mark. Is it true that when you blow up, you get these two and nothing else? I have a theorem which I will probably not be able to prove that uses actually Alt-Caffarelli-Friedman monotonicity formula to prove that these are the only ones for homogeneous solutions. I can give you the ideas, but I prefer to, because I don't think I can make it otherwise. So here is a theorem. Are unique in the sense that they belong to this class. Call it U0. Belongs to half spaces. After rotation, of course. And any rotation of this. So this means rotation of these things and polynomials. And any polynomials with Laplacian being 1. So the proof uses ACF monotonicity formula. You do it like this, just give you the very rough idea. If the solution, if there is no set, so let me just give you in half a minute the proof. So if there is no set when the function u is 0, there is no set of positive volume. Okay? So Laplacian of u is going to be 1. It's going to be a polynomial. So Laplacian of u is 1. U has quadratic growth, because when we blowed it up, it has quadratic growth. Okay? It was C11. You scale a C11 function, it will have a quadratic growth at infinity, because you're just looking at the quadratic part of this. So you have a Laplacian of u, which is 1. There is no set, almost everywhere 1, and it has quadratic growth, so you have to be a polynomial, Liouville theorem. So that part is easy. Now the problem is, what happens if there are sets of positive volume, and let's say an open set, when the function becomes 0? Then you cannot use this argument. And of course, in that case, because it's homogeneous, you get something like here 0, so it has to be 0 all the way in this cone. And then you use the monotonicity formula of Alt-Caffarelli and Friedman, and it tells you very roughly that if your function is not constant or homogeneous, what happens is that you go from R to R1, you actually increase the value of the function. Okay? So you go from R1 to R2, you increase the value with a certain amount. Actually, you can calculate that. I think that calculation even might be in our original papers with Louis, or maybe I took it out, I don't remember right now. But you can actually compute that. And if you go from R1 to R2, you increase it with a certain value. So that means basically, if you go too many times, of course, the energy will be infinite eventually. But the energy is bounded because of homogeneity. So that tells you that this cannot happen. So it means that Caffarelli's monotonicity formula has to be exactly 0 and nothing else, which is a very important fact. Once it is 0, if you remember the monotonicity formula, it contained the derivative of u plus, and then gradient of this to power 2, the integral times the same thing with the minus. So it means that one of these integrals must be 0. If one of these integrals are 0, it means that one of these functions must be 0. And then you get all these directions that the function is going to be 0. And you can prove that this can happen actually in a lot of directions, and your function has to be one-dimensional. There's a little bit of exercises, all these things, actually very elementary, a little bit of exercises. So you get that you can get actually in a lot of directions, so you get just one direction survives. And you get basically that the function is one-dimensional. A one-dimensional function, now you can solve it. That's going to be something like this. And that's exactly this one. So this was the very rough proof of it. So let us accept it. And I will go on with, so now we come to Donatello's question when I'm using that the thickness condition. So far I haven't been using it. And I have the information that blow-up solutions are going to be either this or that, so I want to exclude this. If I want to exclude this, it means I need to assume some thickness condition. So somehow I can just ignore thickness condition also. I can say, I'm just looking at points where the blow-up will be half space. So somehow, of course, I'm putting that condition. But somehow I don't need to discuss that. So from now on, I will just look at the points where the blow-up will be half space. And I will call this regular points. So I want to study all the regular points. Of course, this regularity is very weak regularity. It just says that the blow-up will be a plane. And you see already from in geometric measure theory concept, you can have a lot of things that are coming. All can be below these things. We can have a lot of things. And you blow up this set, it will be a plane. So the blow up is a plane. That doesn't mean much. But in this context, it actually means a lot. Okay, so my next lemma is this, that I want to say that if I take a point which is a regular point with respect to the energy, then this point, you see, when you blow up, it will be something like this. So this means that your free boundary locally is very flat. So you want to use that. So your free boundary locally must be very flat. Because you scale it to the level 1 over r, it means that in a ball of radius 1, the solution is, free boundary is becoming narrower and narrower. And so on this side, you have the function is 0. On this side, the Laplacian of u is 1 completely. And then there is something here in between wiggling, and you don't know what happens. So the idea would be to get exactly this information, which is the next lemma, that the function is going to be 0 and Laplacian is going to be 1. And then what I want to do is take an auxiliary function and prove that my function, if you go like this, u will be monotone in these directions. And you can actually take a lot of directions which are almost close to this normal. First you find this normal, okay? Then you take all these directions very close to that, and you prove that your function is increasing in these directions. What does it tell you? So if you have something here, which is a level set of a function, u is 0, not a really level set, but u is 0 on this boundary, and then you go all in these directions, the function is monotone. And you go in this direction, the function is monotone. So it means that in this direction, your function is a graph. In this direction, your function is a graph. So you have a bunch of directions where your function is a graph. That tells you it's Lipschitz. If you take the balls smaller and smaller, this direction can be made more open. And it means that locally you get C1 regularity at that point. And you can do that with every point close to this, and you get C1 at each point, and so the graph is C1. But you don't get the real C1 norm of it. But you should just say it's C1. So that's the proof I'm going to now make in the next 20 minutes. So the first thing is to prove that when we have this regular point, then if I scale it, I will come close. If I blow it up, I will come to this. But I don't want to blow up. I want to scale it. I want to say, if I take r very small, I will come very close to this. That would be enough for me. And this is exactly the link between global and local. That the globals are like locals are like globals when you go very, very small balls, approximately. And that's enough. So this is basically the link between them. So if you take a regular point or low energy point, then there exists a number epsilon and r0 such that ur, so scale it, minus u0. You can take better norms, but let me take L infinity. This is enough for us. Is going to be less than or equal to epsilon. For all r less than r0. Well, in my notes it's larger than, but it should be less than. So it should be less than. I wrote it larger than here. And moreover, u is positive in xn to epsilon, well, some constant depending on epsilon, intersected with B1. This is not so important, but there is something epsilon dependent, and U is identically 0 in the set xn is less than minus 2 epsilon square root. I have BR here. So in particular, this means that the free boundary is located at a very good place.
The last assertion,
Sorry?
I0 is sufficiently small with respect to epsilon. The last assertion has no sense. Because this is an empty set.
What is that?
If A0 is smaller than square root of epsilon.
I don't understand the question.
Okay, for each epsilon there is A0, but if A0 is smaller than
Now there exists epsilon.
There exists an R epsilon. Yes,
but if it's smaller than
there is an R epsilon.
for epsilon, so
Yes.
it's an empty set.
If what is less than epsilon?
I epsilon is smaller than square root of
If this is smaller than this.
yeah, yes, then the set is empty. Intersection.
Oh, I see. I see your point. Okay. That's a good question. Let me think. But does it matter?
It's empty, so this is full.
So this is true. Yeah. Yes, I don't think. Let me see. You're right. Xn. Okay. Okay. There's an R here.
Oh,
Yes, there's an R here. Thank you. I wrote it in terms of B1, so I tried to write it in terms of BR here. So I'm sorry for that. Or you would say that R is 1 and you have UR. Thank you. Yes, of course. You would say R is 1 and you have UR. So this means that you take B1 and you take UR function. Okay. So there is a direction somehow. So there is a direction. We don't know what this direction is, of course, after rotation. So it can be any direction. Yes.
Are you taking X0 to be
Yes, I'm doing it. UR is, this is already, yes. I think it would be best for me to do it like this. Yes, thank you. Then we skip it. Now I've scaled it to the origin and everything.
You also want a B1 inside of the L infinity norm.
I want one in,
The L infinity norm?
thank you.
They are giving you a hard time,
I'm too tired probably.
man.
So here is the free boundary somewhere. Okay. And now it means that my function u is going to be 0 here, ur is 0 here, and ur is positive. And this is quite obvious because if I let r go to 0 in the limit, I should get this guy. So at some point, the free boundary has to go inside here, the function has to be 0. At some point, everything must be positive here. And you can do that by using non-degeneracy. Use non-degeneracy. Because this argument is not enough, you need an analytic argument, use non-degeneracy and to prove this. Okay. So this is what you get, and this is actually fair enough to. So I don't do the proof of it. This is basically the proof using non-degeneracy. So now I will do the rest here. So the free boundaries. So theorem is free boundary is Lipschitz at the regular points. This is low energy points. And the neighbor of the norm and the neighbor depends on the point. So here is the device that we come back to. So proof, we shall prove that the directional derivative of u is going to be sort of non-negative in very small balls. And this for a lot of directions which are orthogonal to the very close to this xn. So you scale it at some level, then you know that at this level you have something like this. This is one direction. You have E0, I call it xn, and in that direction you take around all the other directions very close to that. You can choose whatever you want to, and then you take a device, and that device will bring you to this, which is what I'm going to do. So, and since you can get this for a lot of directions, and you can just change the point, it means that your function, first of all, your function is going to be graph, and then the directions are changing, so it's going to be Lipschitz graph. So the lemma is this. Lemma. Let me just make a point here, because once I'm done with the lemma, I don't think I will have time to discuss it. So I will just discuss the regularity for close to any blow-up direction. Any or a, whatever you want to choose, blow-up direction, like xn. We choose xn for simplicity after rotation. So it means that you have this free boundary, you don't know what it is, and then you have this direction, xn, and you get that the function is increasing in this direction. So the function is increasing in this direction. Next, you have the other direction. So this is, again, and you have any other direction. This is another E, and then you get increasing. So this together is a bunch of directions in a cone, so you get that. This is a geometric way of saying it's Lipschitz. You get that the set, the boundary of the set, let me put it like this. Gamma is Lipschitz. The boundary of the set when u is 0 is going to be
This is a cone of monotonicity.
It's a cone of monotonicity, exactly. You get a bunch of directions. So this is why the lemma is called directional monotonicity. Okay, so once this is done, once I get it, I will be done with the Lipschitz. So not to write too much and save time. Claim is zero. Effect 0 is a regular point. You take a regular point, you scale your function u, then in the Boloff radius 1/2, you're going to get this. And of course, once you have this, and you know that your function is going to be 0 outside below, let's say, 1/2, and then positive about half, you just integrate this, and you get that the function, the derivative, is non-negative. So this gives corollary. This gives that u is actually going to be negative due to the picture. Because this is 0 here, and it starts becoming larger and larger, so it can never go back. So it becomes really positive. So all the time it's just becoming larger and larger. There is no way out. And you have to really go back and use this. Otherwise it's not obvious. Okay, so the proof of this is just exactly, well, not exactly, but very close to the idea. I think in the paper we wrote the revisited the obstacle problem revisited. Louis wrote, then he had this device, he sourced, I think he wrote, do you remember this? Something like that. Because it's really coming back to this very elementary idea. So proof is if not, then exists a point y such that in the in b1/2 intersected with omega with c de ru y minus ury being negative, strictly negative. Okay, so there is a point. So you assume that this is not positive or not negative, then there is a point when this is going to be negative. Let now w, let's call it r still, be c de urx minus urx plus 1 2n x minus y to the power 2. And this is pretty much reminiscent of the other function, the auxiliary function. This function is now, you use the minimum principle, I think, this time, if I'm not wrong. And then this is in b1/2 with center 0, or y, I cannot read it even, with omega. And then this is negative, you have a little bit more, and wr is larger than or equal to 0 on a boundary of omega r. So what happens is this is a harmonic function. It is negative inside. The infimum must be on the boundary. So the negative, see in the other one we used positive. Now we use the negative because it's negative. There is a point with negative value. Negative inf for WR must be on the boundary of b1/2 and 0. Because it's non-negative on the boundary of omega r, so it has to be on the boundary of br. So 0 infimum of wr is going to be on the boundary, and this is just infimum of u r minus ur. And the good thing again is that on the boundary you have 1 over 8n on the boundary of b1/2. You're going to get a fixed value. The fixed value is very important. This is actually y or x minus What did I wrote? X minus y to power 2. On the boundary, that's going to be r. And this means that infimum of C dEu minus UR is less than minus 1/8. And this is very important, that you have a minus and you have a fixed constant. Okay? So, but this is a contradiction. Because what happens is, but this is a contradiction. This is a contradiction. Since the function UR is almost like x1 plus to power 2 divided by 2. And you think of x1 plus to power 2, which has to take the derivative, take e very close to xn, and this would be like xn minus x squared. And this will be, of course, linear minus quadratic. For very close, it will be, of course, positive number. So it cannot be negative. Okay, because in the blow-up regime, UR is very close to xn to power 2. So it means linear minus quadratic close to 0, it must be a positive number, since U is approximately. This is just computation. Simple. So do you get a contradiction? And that would be the end of the proof, because now we have monotonicity, directional, and then you get Lipschitz, and then you have to go on that. Okay, thank you.
Any questions?
Okay.
Thank you very much for your take over first lecture.
Thank you.
Yeah, thank you.